glad that at least you are here, okay, on time. So half of you are not, right? So okay, so let's begin either way, right? So even for many people are not here yet. So, but we want to start on time, right? So we don't miss the off rate, right? So we will start and then you won't miss the off break. Other people will miss part of the class, right? So, okay, so first off, right? So the links from the notebooks that I'm using here, right? So they are all, you know that there's all the classes are being transmitted, not synchronously, but they are being posted on YouTube, so you can see later. And there's the link of this on the YouTube page, but I guess it's also here on the page of the Orson ICTP website. Okay, so if you go here, you have the classes day by day, and you have the presentations. You have the link for the class, and this attachment here is the notebook. Okay, so you have, it's easy to find the links and so on. Okay, so because of course, since I gave you this class, right? So and then use this notebook and then apply the most useful programming technique, yeah, that is copy and paste, yeah. So and then you can get started easily with that, right? So the second class today is already here, right? So is this link here that leads to this notebook. That is the one that is over here, yeah? So, so let's go for that, okay? Before I begin, do you have any issues or things that you realized later that was missing from last class or that you didn't quite get from last class? Any questions to begin with? Or... Okay, so let's begin. Okay, so so here it is. Okay, so is it? Yeah. So let me turn this off. Yeah. Okay. So okay. So last class, what we did essentially was, okay, given a model with a system of differential equations, ordinary differential equations, now we have the tools to, given a set of parameters, initial conditions, we have the tool to solve numerically those equations. Okay, so given a model, I can find the solutions to that model. Great. But then what is going to happen usually, right? So usually, it's not like I have all the parameters, okay? This is very often, or very often is maybe understatement, it's never the case that you do have all the parameters, okay? You don't, right? So data and information that you have about the world, about the systems that we study, usually under-constrains the model. Usually it is not enough to fully specify all the parameters of any model you want to do. Okay, so this is true for models in epidemiology. It's true for pretty much any model of whatever you think about. Okay, so it's so if you think of science as a puzzle, it's clearly not a jigsaw puzzle where you have a lot of information, a lot of pieces, and you're trying to put it together. It's more like a missing information Sudoku where you don't have enough information. You never have enough information, right? You're always lacking information, okay? So even though you can have a lot of data, you usually don't have all of the information that you really want, okay? So this means that your models are going to, you want to understand their behavior, not for a single parameter, okay? You want, for instance, if you want to know the general behavior of a model, you want to run it for many different initial conditions sometimes, or maybe different parameters. Maybe you have some particular key parameter that is the focus of your study. For instance, you're thinking about, I don't know, some emergent disease. Maybe you don't know what is going to be the transmission rate, so you change the transmission rate and see what impact does that have in your model. Or you're thinking of, I don't know, Now, I don't know if you have to go over a lot of examples about this, or it's pretty clear already. Yeah or no? Yeah? So in general, you're going to have to, to run a lot of simulations in terms of exploring what the model can give you in different circumstances, either because you don't have these parameters, or you want to understand what happens in different situations, even for you're looking at one particular situation, maybe in other situations you have different stuff, okay? So this leads us to what is called parameter space exploration, right? So what is a parameter space, right? So your model has, I don't know, 5 different parameters, okay? This is not a lot, okay? So 5 looks like a lot, but it's not a lot. 5 is a really simple model, okay? So, okay. And then you say, okay, but these 2 parameters here, it's more or less always the same. I don't know, maybe, I don't know, over rate is pretty much constant and so on. But there are lots of other parameters that I don't know for sure. So what is this parameter space? Is the space that, like, you want to understand what, like, when you vary all of these parameters here, I don't know, these other 3 parameters, what happens to the model or with your system for all these different possible situations, yeah? So this is parameter exploration, yeah? And then inside this, there's something that is called bifurcation diagrams, right? So, or qualitative analysis, okay? What is this? This is, and this is, I think it's easier to look at the simulations, but let me tell you already what it is. It's like, what happens when you vary some parameters, what happens is that your model doesn't, of course, if I change a parameter, the model is going to change, yeah? The solutions are going to change. But sometimes these changes, they're not very marked, right? So for instance, suppose for instance, I'm looking at an SAIFR model, sorry, right? If I change the infection rate a little bit, it's going to change a little bit the solutions, yeah? But of course, if you change just enough for the R0 to go from below 1 to above 1, then there is not a small change. This is a dramatic change, yeah? Because now a disease that was disappearing, now it has an epidemic curve, yeah? It spreads, okay? So this is a dramatic change, yeah? So the solution changes dramatically. So this is, essentially, this is what is called a bifurcation. It's when there's a kind of a dramatic change, when there are fixed points that were stable and now are unstable and vice versa, and then the solution changes in a more dramatic way. So how do we go about this in terms of numerically exploring this, right? So the idea is, okay, so let's start with this model here. I'm not sure if Roberto thought about this model in particular. Yes or no? The SAIFR with waning immunity. So this is called, this is actually called the SAIFR-S model, right? So SAIFR-S, yeah? Because now we're so without this omega R over here, this is the SAIFR model, right? So if you think of waning immunity, right? So individuals lose immunity after some time. It means that over individuals that are resistant, right? So that were resistant to new infections, they become susceptible again. Okay, so they go from the R class back to the susceptible class. Okay, yeah. I don't know. Did Roberto talk about this or not? No? Okay, so this is a new model for you, right? So SAIFR-S, okay? So, okay, so this model here, pretty similar to the SAIFR, okay? But then there's this new stuff here. Okay, so we will use the same code as before, right? So here in just copy and paste from last class. Yeah. So it would be actually useful if I just copy and paste here, but I already did this at home, okay? So I just copied and paste the code from yesterday, okay? So here I import all the libraries, NumPy, OGINT, and the plotting library, okay? And now I define the time, I define the parameters here, okay? the total population. I define the initial condition. Once again, the whole population is susceptible except for one infectious individual. And here I have my the function that defines the right-hand side of the equations, right? So how did I do this? Well, I have x. X is a vector with three elements, s, I, and r, okay? And then I have to return the differential equation. So this is the first equation, the equation for s. So I have minus beta si over n. So this is minus beta si over n plus omega times r. That is s2 here, this is r. Okay? Easy? Easy or not easy? Easy? Yes? Everyone follows? Okay. And then the second one is pretty much the same. So it's just this term here, but positive, minus gamma I. And the last equation for r is gamma I minus omega r. Okay? Okay, so this is my differential equation. And now I just solve this calling OG int with the function, initial condition, times, and the list of parameters here, right? And then I plot the solutions down here, okay? So if I run this, just this is not yet an exploration of the parameters, okay? But it always takes a small amount of time. So for people that arrive it later, the link for this notebook is already on the website of ICTP, okay? So if you go for this attachment here, it's the link to this notebook that I'm running, okay? Okay, so this is the solution, okay? So it's population of infectious increases, and then until here, more or less, it's pretty much similar to the SIR, right? But what happens later? In the SIR, over people stay resistant to the disease forever, and then the infection never comes back, okay? In this model, resistant individuals become susceptible again later, right? So eventually I have another peak here, you see? And then another one, and then the situation stabilizes, but with I different from 0. You see, this is, maybe it's not clear from here. Maybe let's draw a grid over here. I think this is useful, yeah. Here, yeah? So now this is much clearer, yeah? Okay, so the population of infectious individuals doesn't go back to 0, so this is an endemic situation at the end of the simulation here. This infection here became endemic, okay? It's permanently established in this population, okay? Okay, and in the middle you have a series of peaks here, okay? So far so good? Okay, so this is what happens with this kind of model. So this is, in a sense, similar to, I think, what Roberto told you about is SIR with vital dynamics, yeah? Vital dynamics, he described it? I think so, yeah? With birth and death. Yes, no? Didn't he talk about it? No? Oh, maybe I'm spoiling his class then, sorry. Okay, so, and what do we want to do, right? So we want to look at this and see what happens for when I change a specific parameter, okay? And what is the key parameter here that I want to explore? I want to explore infection rate, okay? So I want to explore how this model changes with beta, okay? Why beta, right? Well, this is kind of numeric exploration, right? So I'm free to choose any parameter, but usually the choice of the parameter to explore comes from your understanding of the problem or understanding of the system. Comes from what you want to take from the model, right? So it doesn't come from the math itself or from the computational part. It comes from the system, from what you want to study, right? So here I chose beta because I thought it was more interesting to look at disease with different infection rates and so on, okay? So I fix it here, gamma and omega are fixed, okay? And now let's go for this. So what I want to do now, okay, if I change beta a little bit, okay, one time, right? So here it is 2, and now I change it to 1.2, okay? So smaller beta, okay? What happens here? Well, this is a little bit weird, right? Yes or no? Yeah, well, there is an infection, there is an epidemic here, but it takes a lot longer, right? And what happens at the end of the simulation? Clearly, stuff is still going on, yeah? Stuff is still going on, right? So, although here, after 100 time steps, things were more or less settled down, here it's not, right? So the first thing is, well, when I change the parameters, maybe the time scales change, yeah? So maybe what I want to do here is I want to run this for a longer time. Do you agree with that or not? Yeah? So the first thing is, well, maybe run for more time. Yeah? So if I'm running for 100, maybe 200 here. Yeah? So now things look more like they are already settled down. Yes or no? Yeah? Okay. So you see that when you look at a single simulation, it's easy to say, well, the time until you settle down, where you have the solution at a steady state, here is 100. But for different parameter values, this is hard, okay? It's hard to know how long it takes to settle down to a steady state, okay? It's hard. You don't know in general, right? So what do you do in practice if you want to look at the steady state for a range of parameters? You really put a very, very long time to be sure, okay? Yeah? So this is what we're going to do now. We are going to run the simulation here, and I'm interested here. You see, I told you that this goes to an endemic state, okay? So I'm interested in this endemic state, the steady state of the disease after a long time, okay? What do I have to do then? I have to run the simulation for each value of beta, and then look at this steady state, the value of the infections, the number of infectious individuals for a long time for each value of beta, okay? And record this, yeah? But I have to be careful that I have to wait for a long time to be sure that I did reach a steady state, okay? Clear? Okay. So let's do this. So now what I'm going to do is, okay, I will do what is called a bifurcation diagram. Okay, so this is, let's see what goes on here. So now instead of using 100 or 200, I go and put 10,000 here. Yeah, I want to be sure. I don't want to, well, maybe I did something wrong. No, I want to put a time that is so long that I'm pretty sure this is always, I'm always reaching the steady state. Okay, so I'm not going to play, well, maybe 100 or maybe 200. No, let's put 10,000 and be sure, okay? Okay. Okay, now I'm going to choose a range of betas, right? So I'm going to go from beta starting at 0.9. Why 0.9? Because I know that for this model here, the R0 is going to be beta over gamma, and with beta below 1, R0 is below 1, I have no disease, right? So no disease spread. So so I can just start at any number below 1 here, and I'm going up to 2. Okay, okay. And now what I have to do? I have to create a list here to keep the solutions, okay? The final steady state. So what do? For each beta in this list of betas over here. Okay, so I go from beta from 0.9, 0.91, 92, 93, and so on up to 2. For each of those betas, I run the simulation again with these parameters are kept the same, but this one is changing, okay? It is changing. So for each step in the loop, I changing the beta, I calculate the new solution, and I take the last value, x minus 1, so the last point after 10,000 times, okay? Over here, yeah, and keep the solution, okay? So I'm keeping inside the fixed points here, I'm keeping the last solution for each value of beta, okay? And at the end, this is a list, okay? I just convert this list to an array to be easier to look at it, okay? So let me run this stuff here. And before I do something else, right? So let me just print this here, right? So what is this fixed points stuff here, right? So let me begin with the shape, right? So this is, you see, it has 110 lines. What is this 110? Is the number of betas, yeah? the number of betas. So for each value of beta, I have a different set of 3 points. What are these 3 points? Are the 3 values of S, I, and R at the final time for each simulation, okay? Okay, and now what do I want to do? I want to plot this in terms of along beta, okay? So I want to plot beta in the x-axis and the fixed points in the y-axis, okay? So this is this plot here. And you see that, now this is nice, okay? So you see that if I have beta, let me put a grid here again, right? So I should always use a grid because it's easier to see, right? So, okay, you see that for beta below 1, you have pretty much all the population remains susceptible and non-reover, non-infectious, okay? For beta above 1, I start to have more and more susceptibles and reovered and infectious at the steady state, yeah? Okay, so this here at point 1 here, beta equals to 1, this is a bifurcation, yeah? This is when I still have this fixed point zeros, right? So 0, I equals to 0, is always a fixed point. But for beta larger than 1, this fixed point at 0 becomes unstable, and this fixed point with infectious individuals here becomes stable. So I have a change in the stability of fixed point, and this is this dramatic change. Okay? This is a bifurcation, and this is why this kind of plot is called a bifurcation diagram. Okay, but of course you can run this kind of stuff even if you have no bifurcation, right? It's just to study how the solutions change with a parameter. Okay. Okay, so okay, of course I can just run this plot to instead of looking at this is total population, right? So this is 10 to the 6. I can plot the proportion of infectious individuals. Right, so the number of individuals divided by the total population. If I plot just this one, this is the plot I want, right? So this is proportion of infectious individuals at the final solution as a function of beta. Okay, so I see that it goes from 0 here to, for beta equals to 2, it goes to about almost 4% of the population. Okay, so I have a constant incidence of prevalence of 4% of the population. Okay? Yeah, clear? Questions? Yes. Sorry, just one. Oof. Okay.
Thank you. With this new model, with the waning immunity, isn't it possible for us to don't have a fixed point and actually just stay oscillating?
Oh, that's a good question. So in this particular model, no. Right? No, it's not possible. Any values of beta, gamma, and omega that you put here, it's always going to either go to 0, right? So no disease at all, or it's going to oscillate to a fixed point. Yeah? So it does oscillate, but it ends up going to the steady state. Okay. So there's always a positive, stable fixed point. There are variations of this model, so of this model here, where you do have sustained oscillations. Yeah, but in order to do that, you need something that is slightly funny. So Roberto, I know that this one he talked to you about. Remember the stuff about the time from the time to recovery being an exponential, yeah? So you have this in the model, right? So you have the time to you have this stuff here, right? So the time from infectious to recovered, this is minus gamma I, this is linear, okay? So this is an exponential distribution of times with mean 1 over gamma. And the time from recovery to susceptible is also exponential, you see? So this is something that takes, this is an exponential distribution of times with average 1 over omega, okay? If I have a model that is pretty much like this, but with a distribution of times that is not exponential in these 2 parameters, right, in omega or gamma, okay? And this would be a different class of model. It would be, you have to write either a system of a lot of equations or integral differential equation and so on to do this. Then you could have sustained oscillations, okay? But this would be a more complicated model, okay? How do I know this, right? So how do I know that this model here is impossible to make it oscillate, right? So I have to do then some analytical stuff, right? Because numerically, you can keep changing the parameters, yeah? I can run this for a very large range of betas, and I can more or less show for beta that it is impossible. Then I change gamma, and then I change omega, and so on. But then it's hard to prove conclusively that that's impossible. How do I prove this conclusively? I do qualitative analysis. I look at the fixed point and show that it's never the case that both of both fixed points, there are only two fixed points here, both of them are unstable. Yeah, always one of them is stable, or one or the other, right? And then I showed, well, then this means no oscillations. Yeah. So, yeah, you have to do more stuff than just numerical. Yeah. Okay. More questions? Yeah, I think Roberto, yeah, again, spoiling his slides again, right? So maybe I think he's going to do this calculation, but for the, I think for the other model, not this one, for the model with vital dynamics, okay? With birth and death, okay? Good. Okay, so this is clear. Okay, so let's look at something slightly different now, right? So here, I'm talking about bifurcation diagram, and bifurcation diagrams, they are really focus on this idea of looking at the fixed points, the steady state of the solution for large times, and so on, right? Right, but it doesn't mean that you cannot look at other stuff about your model that is not the fixed point. Okay, you can use the same technique for studying things that are not fixed points. For instance, for this exact same model here, right? Instead of looking at what happens for a long time scale, I could be interested in, well, what is the peak of the epidemic? Okay, what is the largest number of infectious individuals I have in this model? Yeah, the first peak, right? I could be interested in that instead of this long-term solution, right? Yes or no? Makes sense, right? Yeah? Right, so instead of doing that, right? So instead of doing this here, I can just take my model, right? But instead of now, I will run again, and again, this is the same structure as before, right? So I have a range of betas here, the same range. I calculate the solution for each value of beta, but now instead of looking at the final solution, okay, what do? I take the second variable here, the second column. What is the second column? The number of infectious individuals, okay? Okay, and I look at the maximum value for all times, okay? So this means that, for instance, for this solution here, I'm looking at I over time here, okay? And I'm looking at the maximum value, so it should take this value here, yeah? So I'm recording the peak. Okay, I'm recording the maximum number of infectious individuals. Yeah? And I would keep this instead of the final solution. Okay? So I look here and I take, okay, this is going to be the maximum value of I for each value of beta, right? So I append this here, okay? And when I run this and plot this, here I have I max over n, okay? So this is the proportion of infectious individuals at the peak. I will see something like this. Okay, so again, let me put a grid here again, sorry. So you see that this model here, the model runs here, are exactly the same as before. Okay, so the same values of beta, the same models, and so the same model and so on. Okay, but you see here, the prevalence here for beta going to 2 is 4%, close to 4%, right? But now at the peak, you see that for beta going to 2, this is close to 16%. Okay, so you see that there's a very strong peak happening in the middle. Yeah? Okay, so this is a different property of the same solution. Yeah? Question? Not can't hear you. Sorry.
The behavior exposed on a beta greater than 1.6, is it due to lack of
Yeah, it is oscillating. That's the question. Right? Why?
is it because of the simulation, like it needs more time, or something like the error, like a
It
small
is.
error between one simulation and another, or is it proper to show that oscillation?
Yeah, this is a good question, right? So I saw this and I thought, well, I could fix this old, but I could not fix this old, right? Because what happens when you look at this, right? You see that there's something weird, right? Because the solutions oscillate, okay, but this is the maximum. So why is this oscillating? Yeah, so one way to look at this is how do you debug this kind of stuff, right? So this looks like a bug, right? I don't know, you don't really believe that this is real, right? Yeah? You were expecting something smooth, right? So what do? Well, you take, okay, so here around after 1.6, right? So maybe let's say, I don't know, 1.9 here, right? So what do? Well, let's take the solution again. So let me create a new stuff here, and let me plot the solution with which beta here? With beta equals to 1.9, yeah? 1.9, okay? And let's plot this. Let me copy this. Just so I don't have to write all. Again, the first technique and main technique in programming, right? So copy and paste, okay? Over here, yeah? And you see, actually, I run for 10,000 steps, but actually everything happens really quickly in the beginning because beta is large, yeah? So let's zoom in here. How do we zoom in? We just limit the stuff here to go from, I don't know, this is, let's go to 100 perhaps. This doesn't change the solution, it just changes the plot, the region of the plot, okay? So you see, actually, the maximum is here in the first 20 time steps. Yeah, so maybe let's zoom again. And you see that when you look at in this region here, so this is between 12 and 20. So let's, yeah, and you see that in this region here, the time step that I'm using for time, here it was up to 10,000 in time steps of 1. And you see that the dynamics here is so quick that it's already, can you see that the graph is a little broken? Yeah? So maybe what is happening is that I'm not taking accurately the value of the peak because the time step is too large for beta large. Yeah? Well, so how can I solve this? I can just take smaller time steps. Yeah? Okay, so I go here and, well, yeah, that's easy, right? I run this again, I run this again, and now it's perfect. Nice?
Perfect, thank you.
Yeah, this is profoundly satisfying. Yeah?
Yes.
Okay. Okay, nice, people. Yeah? So this is an example of the kind of stuff that happens when you do this kind of plot, because sometimes the plot looks a little ugly, and you don't know why. Perhaps it's because you didn't wait long enough if you're looking for steady states, if you're looking for peaks or things that happen in the middle, maybe your time step has to be smaller in order to get the details or in order to pick accurately the peak value and so on. Okay? Nice? More questions? Yes. So people can hear you, even the ones on the back. Yeah. You have to turn it on. Okay. Well, yeah, just speak closer.
Yeah, no, sorry. You're working with the maximum, right?
Sorry?
You're plotting the maximum value of I,
Yeah.
right? Over N. So, I mean, there are some mathematics when you look at the system that can tell me that this shouldn't oscillate.
Yeah.
Yeah, I mean,
Yeah.
if I know mathematics, this should say that it's
Yeah.
first derivative, it's continuous, right?
But do you agree that even if you couldn't imagine that you have a system with lots of equations, okay, not 3 equations, because this one is pretty easy to find the fixed point, and you see that the behavior of I star, right, the fixed point of I with respect to beta is a linear thing, right? So it's very easy. But suppose that you have, I don't know, dozens of equations, right? You don't know how to calculate the fixed point. It's too many equations, right? Even then, you would be a little bit suspicious of that. Yeah? Or no?
Of course.
Yeah. Right? So it's not that you know for sure because you made the calculation. You're just suspicious because it looks weird. Right? Sorry, I'm interrupting your question, but it is in this direction. Yeah.
Yeah. Oh, okay, I understand. Yeah, okay.
That was the question. Sorry, I interrupted you, but I guessed it right. I guessed it right.
That was
yeah?
the question. If I can take the system and I do some math with it, and then this could be a function that it has its first derivative continuous. So just that was the question. You answered it and gave a little more.
Sorry?
If I could take the system and then I could do some mathematics, analyze it, and know for sure that this curve has its first derivative continuous, so it doesn't oscillate with
okay.
those.
You cannot oscillate. Okay. Yeah.
Yeah.
But you know, the work you have to do, because, for instance, this is IMAX, okay? This is very hard to do mathematically, right? The other plot, it was pretty easy, right? So it's a calculation you can do in 5 minutes, okay?
Yeah,
but this one is not, okay?
Yeah, I mean,
this one is hard.
We could, I don't know, derive an implicit function. And
Yeah,
just say,
exactly. That's what I'm
say
saying. It's
oh,
possible.
it should be continuous.
Yeah, that's
Okay.
what I'm saying. This is possible to do analytically, but it's hard, okay? Hard. Because this you have to look at the solution in the phase space and so on, and you won't find an explicit solution, so you will be able to find some properties, but not the exact solution. It's hard, okay? So it's possible, but then how much time did we take to find this plot here? Yeah, it was like copy and paste, change the maximum here to take the maximum instead of the final solution, and in 5 minutes it's done. Yeah, and it's 5 minutes for a system with 3 equations, and it's the same 5 minutes in a system with a dozen equations. Once I have the dozen equations running, right? So of course you have to implement the model. But once the model is implemented, looking at this analysis is pretty easy, no matter how complex the model. Yeah. So this is really powerful. You see? The thing is this. The math of qualitative analysis, of looking at fixed points and so on, it doesn't scale well for many equations, right? But this works with how many equations you may want, okay? So this is nice. More questions? Okay, so moving on here. So okay, so this is what I just showed you. Okay. Yeah, I had the question here. Yeah, okay, so let's do something else now. So I want to do something that, because up to this point, I was only looking at models that were what we call autonomous, right? So what is an autonomous model? It's a model that doesn't change explicitly with time, right? So you see that my model equations here, okay? My model equations over here, they were always, really should the index, right? So, yeah. Well, this helps a lot, right? So, okay. I just I don't keep this open just so you can see more of the screen, right? But this is really useful to navigate, okay? My model equations here, of course, the time appears because there are the time derivatives over here, but you see that the right-hand side here doesn't depend explicitly on time, right? So it only depends on time through the dependent variables that are S, I, and R, okay? But then if I have a non-autonomous model, for instance, what I'm going to say here is, well, suppose that beta, my infection rate, is seasonal, okay? I have a seasonal disease, something that is easily transmitted parts of the year, or I don't know, maybe some other factor. I'm not here talking about any specific disease, but this is pretty common occurrence, right? So that you have times of the year when transmission rates increase, okay? Okay, so if you do this, you can arrive at seasonal epidemics where the seasonal is really infection rates increase or decrease seasonally, okay? And then what I'm going to say, I'm going to use the same model. I could probably, let me open paste this here because it really bothers me not to have the model written up here, okay? So, yeah, so I'm going to use the same model as before, right, over here. Yeah, so this is the model here. But now this beta here is not just beta, okay? It's actually beta of t, okay? So the same model as before, but now this is beta of t. So it changes with time, okay? So yeah, now this is better, right? So this is the same model as before, but beta is now a function of time, okay? And I want to do something that changes seasonally, okay? So I'm just going to say that this is a constant. It is 1 plus a constant alpha, that is the amplitude of the oscillations around the mean. So beta 0 is going to be the mean value of beta. And I have oscillations with a sign with a certain period, big T here, okay? Yeah, so this is period T, right, of beta of t, right? So if I just plot, let me be just plotting beta, right? So beta is this expression here, you see? So here I use it beta equals to beta 0, 2, and large t here is 52, okay? And if I plot this, it's just, you see, the average value here is, yeah, I should start putting grids everywhere, right? So you see the average here is 2, and the amplitude, right? So from minimum to maximum is what? Is this guy here is 0.2. What is 0.2? Right? It's 0.2 is 0.2 relative to the mean, right? So what is 0.2 times 2? It's 0.4, right? So the amplitude goes from 2 to 2.4 and to 2 minus 0.4. That is 1.6. Okay? So this guy here controls the minimum and maximum of the oscillations. Okay, and this t here means the period here, right? So I complete a full oscillation here after 52 times here. Okay? Yeah? Okay. So this is beta of t, right? And now what is going to happen to this model? So without looking at the solutions, yes, still, right? I'm still didn't run the model yet. What do we expect from this? Well, now you are forcing externally the system, right? So the beta changes with time. So I expect what? I expect there to be oscillations with time always in the model, yeah? Because I'm always changing the value of beta, okay? So this model here, it's not going to go for, it's not going to stay at a steady state, yeah? It's pretty much impossible because I'm always changing the system. Yeah? Yes or no? Does that make sense or not? Yeah? Okay, so if I look at the solutions to this model, right? So how do you do this, right? So I do the same thing as before. I define time, define the parameters here. Now instead of just beta, I have beta 0, that is the mean value, the amplitude. Actually, this is half the amplitude, technically, right? So the amplitude is maximum time minus minimum. 0.2 is only half of that, right? So, okay, and gamma and omega. And now you see that this SIR actually should be SIRS, right? Season. I only change the value of beta for each time, and then everything else stays the same, okay? Because beta is a function of time here, okay? Yeah? Pretty easy, okay? Okay, and now I just run this model again, right? So simulate it numerically here, okay? And here it goes, right? So what I want to be careful about is this list of parameters is getting longer. I have to be sure that this appears in the same order as it appears over here, right? So what is the technique to be sure that it's the same order? Copy and paste, yeah? Okay, and now I plot this, okay? So here's the plot, and you see that beforehand I had oscillations after some time here that we're settling down to a steady state, okay? But now I no longer have a steady state, okay? I no longer have a steady state. So I have now oscillations always, okay? Why? Because I have beta varying with time, yeah? And what are the periods of these oscillations? It's close to 50, right? So it's probably 52, right? I chose the period here to be 52. This is 52. Why 52, right? So I was thinking of time in terms of weeks, and 52 weeks is 1 year, right? So, yeah. Okay? So, more or less expected, people, yes? Yes or no? Nothing too surprising, but you see now that the shape is now a little bit funny, right? Because what do I have here is I actually have two oscillations in the system, right? One is the oscillation of beta, right? That is an external oscillation that I'm imposing here. But I also have an internal oscillation because you see, the model that I had beforehand already had oscillations. You see? Okay, after some time, the oscillations died down. But I do have oscillations here, okay? Okay, so it means that I have two oscillations in the system. When you have two oscillations in the system, physicists start to get happy, okay? Because you now have two oscillations, then funny stuff begins to happen, right? So, like, for instance, I can have a coupling of these oscillations. Then you can have, for instance, resonance. Yeah? Resonance. Everyone knows what a resonance is. Yeah, or at least not, even if not mathematically, maybe from an empirical point of view, yeah, when two frequencies are close together, they interact with each other with a positive effect of making the oscillations much larger. Yeah? Okay, so you see that, for instance, I can have, in this system here, I can have oscillations, and I do have oscillations, but I can also have resonance, okay? How do I check for this? Well, I can change the period of one of the oscillations and see if there is some period where the amplitude changes, the amplitude grows, okay? How do I look at the amplitude, okay? Now things are getting a little bit weird because now what I want now is no longer, if I want to see the amplitude of the solutions, it's not enough to look at the final solution here after a long time, because I'm just taking one point along the cycle, right? So I'm not looking at all the points. I'm looking only at the final point. It would be anywhere along the cycle, right? Yeah? And I don't want just to look at the maximum value that is going to take the peak here in the beginning. What I actually want is I want to wait for some long time and then see the minimum time, the maximum times the minimum for these oscillations here. Yeah? So it is like a steady state, but it's not steady, right? So it's a steady state that oscillates, right? So this is what we call the long-term dynamics, okay? But the long-term doesn't need to be an equilibrium. It can be something that is still changing in time, okay? So how do I do this, right? So I'm going to do something that is, instead of just taking the maximum here or just the last point, I'm going to take the minimum and the maximum, but not of the whole solution, only the solution after a long time, okay? Does that make sense? So maybe let's run this again for a little bit more time here. Okay, so I will wait some time. Okay, and you see that this is periodic. yeah, as we expect. So I'm just going to cut out the first part of this stuff. I'm going to cut out and going to take the last part here, and I'm going to say, well, I want the maximum minus the minimum. Yeah, and this is going to be the amplitude of the prevalence. Okay, the maximum prevalence minus the minimum prevalence to see how this changes when I change parameters. Which parameter? I'm going to change something that is related to the frequency, and here I'm going to choose t. Okay, so the period of beta. Okay. Yeah. Here. This doesn't make a lot of sense biologically, okay? Usually, if I'm saying, oh, well, this is a seasonal change, and the seasons are, I don't know, yearly, it doesn't make a lot of sense to change the length of the year, yeah? So, so here I will ask you to excuse me, because this is just an exercise, okay? Yeah, doesn't make a lot of sense, but I'm going to change this parameter for now, okay? So I'm going from, I don't know, 4 to 100, and now for each value of large T, I calculate the solution again, okay? And what do I do here? I look at the solution for the for the infectious diseases, infectious individuals, only the last 1,000 time steps, okay? So you do know that this is stuff with negative indexes, right? So this is from the minus 1,000, minus 1,000 is count 1,000 from the end to the beginning, right? So I count 1,000. This is time steps of size 0.1, right? So this is the last 100 points, right? So 100 time steps, not time steps, but 100 times here, okay? So from 1,000 to 900 here, so I look at this window of time here, okay? This last 100 points. And in this last 100 times here, I look at the minimum, okay? And I look at the maximum as well. And I record this in this list of Xmin, Xmax, okay? Okay, and then at the end I have the Xmin and Xmax. So let me run this. So let me print one of them, right? So, yeah, it is taking a little bit longer now. Yeah, okay. Yeah, here it is, right? So you see that now I have an Xmin for each value of T, of large T, and an Xmax for each value of large T as well. And what do? I plot both of them together, okay? So I do this, right? So I'll plot here this divided by n, just because I want to see the proportion to the total population, okay? And you see, this is the minimum, and this is the maximum, yeah? And what does this mean, right? So let me put that region. What does this plot mean, right? It means that for each value of large T here, I have that the population of infectious individuals. For instance, if I take T also 60 here, what does this mean? It means that the final solution is oscillating between these two values here, right? I don't know the shape of the oscillation, but I know the amplitude of the oscillation. It goes from around 0.022% to close to 6%, okay? So it is oscillating between these two values here, okay? Actually, we run the simulation at 52 here, right? So this simulation here, right, is this one here. So this is this amplitude here, because this is SIR, right? So if I plot just I over here, it's easier to see. I have these solutions that are oscillating between these two values here. Is it clear, people? Yeah? Yeah, so this is how you analyze oscillating solutions, right? And you can do different stuff, right? And look at minimum and maximum if you're interested in the amplitude. If you're looking at, if you're interested in averages, then you can take the average value for the solution, or you can take the median. You can take some aggregate quantity, but it's hard to really change parameter and look at the shape of the oscillation, but you can do stuff like the average, the minimum, and the maximum, and so on and so on. Okay, so this is how you deal with oscillating solutions. Okay, and of course, what you see also in this plot is that you see a peak here. Yeah, so there's some value of t here that is where you have a much larger amplitude than for other values of t. Yeah, and this peak here, this is what we call the resonance frequency. Okay, or this is a period, right? So, but this is where there's this. Probably I won't do this right now, right? But if you look at the frequency of the original equation without this external forcing, right? So this this frequency here is probably close, either close to this is always the case, right? So this is either close to the original frequency or close to the half of the original frequency, right? So it's always some multiple of the original frequency, okay? So, and this is where you have a resonance, okay? So this looks like a bifurcation diagram, but it's not exactly a bifurcation, so this is usually called a resonance diagram, okay? But yeah, it's pretty much the same spirit, okay? Nice? Yes? Question? Yeah.
It's possible estimate the amplitude from the data?
Varying beta.
No, the alpha,
Alpha?
the amplitude. Yeah.
Okay. You want to change alpha instead of beta, instead of t. Yeah. So yeah, you can just So
But
this is.
from the data, the real data.
So here we plot the amplitude. Okay, we plotted them. Actually, we plotted the minimum and the maximum, right? The amplitude is just the difference between this di and this di. Yeah. But you want to change. You want to go back to this model, and you want to change. Instead of changing t, you want to change alpha. That's the question?
No.
Oh, no.
If you have the real data.
Real data. Okay.
Real data. Okay.
Real data. Well, now everything is complicated. Okay. Okay.
So from the real data, it's possible to estimate the value of the alpha, the amplitude of this.
Well, the alpha here, right? Alpha is not what you see. The data usually you have epidemiological data. Okay, so you don't even have prevalence. Well, you can have prevalence, but in many cases you have incidences. Okay, new cases. But you don't have, because this change that we included here in beta, right? I changed it beta. Okay, so beta. This alpha here, this guy here that I changed here, this is beta. This is infection rate. Okay, so this is our contact rate and so on. Okay, we almost never have data on this, right? Because this is a parameter. Okay, we don't usually measure. It's hard to measure parameters directly. Okay, but yeah, we can look at the prevalence data and measure the amplitude, the period, the frequency, and so on of the data. Yeah, and then you can compare this to what your model gives. Yeah, but it's hard to measure amplitudes and so on of the parameters themselves. Okay, unless the parameter is something that you can observe directly, like for instance, over rate is something that we do observe more or less directly, right? So we go and look at a person that has the disease and count how long it takes for them to recover. But infection rate, on contact rates and so on, it's really hard to measure. Yeah, it's not impossible, but it's hard. And then to measure this along the year is even harder, right? So I don't recall seeing someone measure this Of course, you can have indirect measures, right? So, for instance, if you have, and I'm already spoiling a bit some of the topics, right? So, some of the projects, if you have a disease that is transmitted by vectors, maybe amount of vectors is a proxy for transmission rate. Yeah. So, if you're a vector, right, a mosquito and so on, if it has a large population during part of the year, then transmission rates will be larger during that time of the year. Yeah, but this is kind of a proxy for transmission, not transmission itself. Yeah? I don't know, maybe I misunderstood your question. This is what you're asking. If you can measure somehow this amplitude. Yeah, don't you want to try to phrase or think a little bit more later? Okay, can go back later to this.
I think we think beta depends of the temperature,
Yeah,
and this oscillation can be minimum and maximum temperature, and the transmission depends
yeah,
that
yeah, sure.
in this not intrinsic
Yeah,
of the disease.
yeah. Yeah, it's not that dependence in time is usually through some other variable, right? It's not that, yeah. It's like, depends on humidity, temperature, abundance of vector, abundance of, I don't know, even sometimes
This is amplitude.
human movement, or, yeah, in case of places where you have, for instance, vacation where a lot of people go to some place, and then that some place now has a lot of influx of people with some disease, right? So, yeah, or world air migration and so on, right? So it's not right, like, it's never intrinsic, right? So beta contact rates increase with time or change with time, not because of something intrinsic. It's always mediated by some process of ours, right? Yeah? But then you have to model these processes if you want to go into detail, yeah? Okay? Yeah. More questions? Yeah, over there. Can you speak closer to the mic?
Would be the threshold modified when we introduced oscillating epidemic transmission rate?
You mean the threshold for having
Yes,
the disease? Yeah, this is a good question, right? So, for instance, we know that for this model here, we have just seen in the beginning of that class that that for beta below 1, you don't have the disease anymore, right? You don't have any, for long term, you don't have any infectious individuals. Now, if you have oscillations, if the average beta is 1, or is just above or just below 1, is it the same? Is the average what matters? I don't know. Then you have to explore this model. Yeah? I don't know if you're asking me to do this right now, but maybe you can just do yourself. Yeah? This is an interesting question already. Yeah? Everyone got his question. Is the average that matters for elimination or not of the disease? If I have a large amplitude in beta, but the average is close to 1, right? So if I just above 1, I have the disease, and just below average of 1 in beta, the disease is eliminated, or is not just the average? Yeah? I don't know. Yeah, I have to run some simulations. Yeah? Okay. Yeah, I don't have the answer ready. I guess it's the average, yeah? At least for a sinusoidal thing like this. If you have a very asymmetric a very asymmetric shape, I'm not so sure anymore, but it should be the average because essentially it's a linear process close to 0, so it should be the average, yeah. More questions, yeah.
Like, my question is close to the one he asked. Like, can you put the Imax and min graph again?
The first, the one with.
No, I think it
no,
was
not this one.
the last one you showed.
This one, the IMAX or the seasonal one.
The seasonal one.
Ah, the seasonal one over here. This one.
Yeah, because I mean, it might be a very naive question, but this graph, it's somewhat symmetrical at the beginning and at the end. And there's this interval at the middle where it's not symmetrical.
Yeah.
Is this something common, or is just because of the...
It's very common, right? Because the minimum is, it cannot go below 0, right?
Mm-hmm.
But the maximum is, this is not getting even close to 1, right? So the maximum is 1, but it's not getting close to 1, right? So, so it's really easy to be asymmetric when you're very close to the minimum but far from the maximum,
Okay.
right? So, yeah, you expect this, yeah? More questions? No questions? Yeah.
Sorry. When you have oscillations on beta, R0 lost his capacity to predict the outcome. I mean, when we have R0 below 1 and above 1, we can predict if the disease extinct or not. But now beta oscillates, so maybe...
What is R0 now?
What?
What is R0 now?
R01 is when
No, but in this case, because R0 would be just beta over gamma. But now beta is a function of time. So what is R0?
That's what I mean. It cannot predict the outcome anymore.
So this is an open question. Yeah. So this is. You know that if you have a disease, if you have an introduction of an infectious individual in a population that is completely naive, okay, all individuals are susceptible. Well, if this introduction happens when beta is such that R0 is above 1, you will have a spread. But if this introduction happens when beta is such that R0 is below 1, then you hope that this doesn't spread. But then you don't have a single R0, right? You have an R0 that depends on time. So it's not that you cannot predict anything, it's not that you cannot say anything, but the situation is more complex. Yeah?
But you say it depends of the initial conditions. In which point of
at which point in time? Yeah?
Okay.
Because R0 is actually changing time.
Okay.
Yeah?
Thank you.
So, yeah, I think that's more difficult. That's harder. Okay.
You can do anything of this analytically?
Yeah, you can. Of course, the model solution itself is hopeless, okay? But you can still do analysis around the fixed points even with fluctuating parameters, okay? Because essentially you have, how do you do analytics with this, right? So you usually linearize around a fixed point, yeah? Okay, and then you look at stability analysis with the eigenvalues and so on, okay? So this is with no dependence on time. With dependence on time, it's pretty much the same, but now the linear system that you have to analyze is a linear system with periodic coefficients. And this is the kind of stuff that you can do as well, right? But it's going to be more complicated. But you can solve linear systems with periodic parameters as well. It's harder, but yeah. Okay, yeah. More questions?
I have a question in the similar direction. Could this modeling of parameters with the explicit dependence on time change the nature of the phenomena? For example, with the constant P, we had two fixed points, and one was stable and the other was unstable. Could this change of modeling beta, now it's a function of time, could it change the
Well,
the stability of the fixed point, or now we have three fixed points, not two? No.
well, in a sense, when you have something that depends explicitly on time, in a certain way, you don't have any fixed point anymore,
No.
right? Because, well, yeah, you cannot have, yeah, okay. But in a sense, I understand what you're trying to ask. I think it's like, of course, the behavior of the solution is going to be influenced by what happens at each point in time. Then, in a sense, well, you're not really creating new fixed points, or, of course. So, for instance, because beta is changing from a minimum to a maximum, okay? At a minimum, you have this some fixed points. At the maximum, you have other fixed points. You can have like all the fixed points that it's always with some constant values of beta, yeah. And then you can look at what are those fixed points. But of course, you're not really creating new fixed points. You're destroying fixed points. But you expect your solution, because at each point in time, you are going in one direction with the dynamics, okay? And this is influenced by the fixed points, but you're not really creating or destroying anything. But you can change stability, right? So I don't know any example in epidemiology that is so dramatic, okay? But in physics, there's this famous example with the inverted pendulum. I don't know if you heard about this. Inverted pendulum is what happens if you have a pendulum upside down, okay? So you have to have a pendulum, right? So but then you put it upside down. Of course, you have to use something that is hard, not a rope, yeah? So that it can stand upside down. But then if you make the point where you usually, from where you hang, right? So if you make this point here oscillate very quickly, you can stabilize the pendulum upside down. So this is a fixed point that is unstable usually, but if you have weak oscillations, you can stabilize it upside down. So it's possible to stabilize a fixed point that is usually unstable by having some strong dependence on time, yeah? So, but this is kind of in the context of epidemiology, this is a little bit contrived. I don't remember an example where you have an unstable fixed point. This is hard to see, yeah?
I guess
okay, but it's possible in principle, but I've never seen this in epidemiology, but yeah.
I guess maybe our formulation of my question was the idea of these. When we introduced the time dependence explicitly, we just got these external oscillations. The idea that was in my mind that, so it means that we had something such as the real phenomena or the intrinsic oscillations. So how far can we go by putting this external thing? Are we destroying the phenomena? Are we modeling it better? This idea of how much are we changing?
It is not, well, the structure is always pretty much similar, right? So if you have a disease that behaves in a certain way in a constant environment, when you make because usually what do you, this is stuff about constant environment, for instance. doesn't ever exist in real things, right? So everything is always changing, yeah? So, so when we model stuff like, well, all the parameters are constant, it's always a model choice, right? So it's always like, well, I'm looking actually at the average, okay? So beta constant is actually the average beta over time, over space, over population, so on, is an average, right? So we are already working with averages. When you say, well, this changes with time, now you are working with something that is not the average, but it's not changing the intrinsic stuff, right? So it's thinking in terms of destroying something is weird, right? So it's usually what happens is just that you can use, what I mean is, you can use your knowledge about what happens with constant parameter, with average parameter, to inform what you expect from the situation where you have oscillations in the parameter, okay? It's not like completely different. It's just that some stuff that you used before, like stability analysis or analyzing steady states, they don't work anymore because now you don't have steady states anymore. Fixed point analysis is harder to do or it's impossible to do and so on. So yeah, okay, but it's not like, well, everything changed completely. No, no, yeah. More questions? Yeah, so this stuff is nice, right? So changing time, okay. Okay, so I think we are close to ending, I hope, right? So because we are running out of time as well. Yeah. Okay, so just to give you some more stuff for thought here, right? So now what happens? So I told you that usually you don't have all parameters, right? So of course I was being really nice, right? Because what usually happens is that you don't have a lot of parameters, right? It's not that you don't have one parameter. You don't have many parameters, okay? So, so of course, it's really hard to explore a large parameter space. I mean, when you don't have a lot of parameters. Usually, you want to be able to fix, or to fix, when I mean fix is find some reasonable value for some of the parameters, right? But what do you do if you want to explore two parameters, for instance, two parameters at once, right? What do I mean by at once? Of course, for instance, in our example, I want to explore in the SIRS model what happens when I change beta and when I change omega, okay? Of course, I can run a bifurcation diagram on beta with omega fixed, and I can do another bifurcation diagram on omega, varying omega with beta fixed, okay? This is nice, this is okay. But maybe you think that the interaction between beta and omega is important, right? So that when you change both at once, you can have some new stuff, okay? This is not a good example because you see that nothing interesting happens here, okay? But maybe it would in your model, okay? Maybe you have two parameters that you think that their interaction itself is important, okay? So you want to change not one with the other fixed and not the other with this one fixed. You want to change both together, yeah? So what do? Well, you can do the same thing as before, right? Instead of changing in just one direction, you change in two directions. And now, what you expect to have? You expect to have one axis is beta, the other is omega, and now your solution is in the third dimension, yeah? So you want to plot in 3 dimensions, okay? So, so what is left here? You need to learn how to do a plot in 3 dimensions, okay? So in terms of programming, this is not so complicated, okay? So once again, I set T for a very large time. I have my range of betas, okay? Here I put a larger step size because what happens, for instance, if I was varying only beta, if I put 100 values of beta, that's okay. There are not a lot of simulations. If I run a bifurcation diagram on omega, I put 100 values of omega, that's okay too. But if I do the analysis with both of them at once, okay, I will have all combinations for all values of beta with all values of omega. So if I have 100 of each, it's 100 times 100, yeah? Because for each value of one, I run for all values of the other, okay? So I have 100 times 100 is now 10,000. So now this becomes 10,000 simulations. Okay, so I have to be careful that at some point simulations will start to take a long time. Okay, so here I put a little bit less simulations here. Okay, so this is the range of betas. This is the range of omegas. Okay, and let me run this over here just to. Oh no, let me break this here because I don't want to run all the simulations yet. Okay, so here it is, okay? So I have 20 values of beta, 24 values of omega, okay? And now I want to do all of them against all of the other, okay? So I have to do a grid, okay? So this is mesh grid function. It takes the values of betas and the values of omegas and gives me back a grid in this two-dimensional plane with the values of beta and the values of omega, okay? So let me run this again, okay? Here. So I had 20 values of beta and 24 of omega, and now this B and O, these are their grids, okay? So I have two grids with 24 by 20, okay? What is this? It means that I have, in two dimensions, one is, let me print one of them, right? So print B here. So you see, these are the values of beta, right? So this is always changing along the lines and constant over the columns, because you have beta for each point. I have in the column, I have all values of beta are the same, but it changes along the lines. And for omega, is the other way around, right? So I have here, it is constant along the lines and changing along the columns. Yeah, so it's a grid where for each point in the grid, I have one value of beta and one of omega. The values of beta change along the lines, and the values of omega change along the columns. Yeah, makes sense or not? It's a little bit weird. So maybe let's let me plot something here, right? So this is our P color. Actually, it's pt.p color. Yeah, just so you see the shape of this stuff. You see, so this is omega, you see? This is beta and this is omega, right? And if I plot B now, it's like this, yeah? You see the change, the difference between the two? So both of them are in a grid, but B changes along the lines and omega along the columns, okay? And I will use this now. This here is the fixed point, okay? So I will have this guy be a bunch of zeros in the same shape as this grid here, okay? So this will be a grid, this IFP is going to be a grid of zeros that has the same shape, that is 24 by 20, okay? So zeros means copy the shape, okay? And now for each value of I and j, that is the number of lines and the number of columns, I'm going to say, well, run the simulation again, but with gamma and n are the same as before, but now beta is bij, omega is oj. Okay? So this is going to take, so for each point here, I take this point here. This will be this value of beta and the same value of omega from the grid of omega. Okay? And now I run this for a long time. Where is it? 10,000 here. And I take the last value, okay? I take the value of I here, looking just at I, okay? And now IFP ij, okay, this value in the grid is the value of I at the final point in time, okay? When I run this, I will have now the values of I, and I'm going to plot this value of I divided by M, that is the prevalence in the population of infectious individuals for a long time. So this is the steady state again. But I'm going to put this in a P color, right? So this is a color plot. Okay, so this means that when I vary beta, okay, for beta close to 1, I have this close to 0, and as I increase beta, I increase the value of I, right? What is weird here is that it doesn't change with omega, yeah? Because, well, omega is not really affecting too much the incidence rate, the prevalence, right? So omega doesn't change the prevalence, okay? So this is, yeah, this is not so fun, right? So omega doesn't have a strong input. So you can use this to say, well, beta is really important for final prevalence at the steady state. Omega is not, okay? You see? Nice. Of course, you can do the same stuff, but now with a surface. So this P-Euler here is to plot this color plot here or heat map, okay? If you want to do the same stuff, but now using a surface, a 3D really, right? You just use this stuff here, right? So you have to create an axis that is a 3D axis, and now you use this function called the plot surface, again with B, O, and this I over M, and now you have a nice surface plot. Yeah? So this is beta, omega. You see once again that it doesn't depend on omega, okay? You see that this is more or less constant here along omega, but it increases with beta over here. Yeah? Nice? Nice, okay. And finally, if you want to plot a line in 3D space, so for instance, what if you wanted to show the trajectory of the solution SAIFR in 3D space and use this, right? So I run the simulation again, right, with the original values of beta and omega, with time going up only up to 200, right, to not be too long. And now, once again, this is the same as before, right? So I create a 3D axis, okay? But now I use this plot 3D. This plots a line, okay? What do? I put the values of S, of I, and of R. These are small s, I, and R because I divided by n here, okay? So these are proportion of the population, right? And this is the trajectory of the solution, okay? This is SAIFR. My initial condition is here. I have S equal to 1. I and R are both equal to 0, or not equal to 0, right? I is 1, right? It's almost impossible to see, right? So this is, I is very close to 0, but then the I increases, and then R starts to increase as well, so it starts to go to the back, right? So because R is in this direction over here, and then I start to have oscillations here, and I go to a fixed point here in the middle. Yeah? Okay, so this is slightly harder to see, but yeah, this is what would be the phase space plot in 3 dimensions. Okay, nice. So this is just an illustration. So if you want to do 3D plotting, this is how you do it. Okay. Questions? What do you do if you want to plot in 4 dimensions? Well, you need to call the aliens, right? So, yeah. Questions? Or are we ready for coffee? Yeah? Yeah, you did have breakfast, right? Or are you already skipping breakfast to eat? Yeah? Okay, people. So that's it for now. Remember that all the links for the notebooks are on the page of ICTP course over here. So you can get those notebooks here. For each class, you have this attachment here. And you can already preview tomorrow's class, I guess. Right? So it's over here. And that's it, right? So thank you. Oh, yeah, I think